We consider again the sphere of radius 1 centered at 0, 0, 1, x and y both positive. In other words, the first octant part of this sphere has density function just plain 1 plus y as before. We want to calculate the moment of inertia of this sphere about the z-axis. Now we've already sketched our typical volume increment, delta x by delta y by delta z, containing sample point xi star, yj star, zk star, and that volume increment might look something like this, very roughly drawn, lying above some region of the xy plane, which I won't sketch, having sketched it a number of times. To do the moment of inertia, we've got to add up the mr squareds, r being the distance from the axis. The distance of this particular volume increment from the z-axis is just this distance here, perpendicular to the z-axis, and it coincides with this distance down here in the xy plane, which we easily see to be the square root of xi squared plus yj squared. This segment here being congruent to this segment and being the hypotenuse of a right triangle with sides xi star and yj star. So that the mass of the increment being, call that delta mijk if we wish, and that's simply delta of xi star, yj star, zk star, multiplied by delta x, delta y, delta z, and we let this, we form this sum and let it approach the integral, and the integral that we get is the integral from 0 to 1, from 0 to the square root of 1 minus x squared, and from 1 minus the square root of 1 minus x squared minus y squared to the square root of 1 minus x squared minus y squared. And that'll be the integral of our delta of xyz function dx, dy, dz. Actually, in this case, dz, dy, dx. And we've seen the reasons for that order with these limits. And so that's just the integral then of what? First of all, we're going to have to do mr squared. Now perhaps I should have written down the expression for mr squared, but it should be clear that this is the mass of our increment and this is the r for our increment. So mr squared is just going to be our density function, which is 1 plus y sub j for the increment, and in the limit as everything approaches 0 it becomes our 1 plus y. Our r squared is just x squared plus y squared, and our volume is dx. Let's do this correctly. Okay, this should be dz, dy, dx. And this integral would not be a particularly difficult integral. We're not going to actually go through the process because we've illustrated all of the necessary techniques in previous examples. But I do want to use this as a kind of a segue into the idea of the cylindrical coordinate system. So we're going to look at this situation as we might see it in what's going to turn out to be cylindrical coordinates. And cylindrical coordinates, we're going to have a z-axis, and we can draw our x and y axes here. But we're going to consider the coordinates of our point down here now to be our theta. So that in the XY plane we have distance r, and that was a bad place to label that, and angle theta, and that's labeled so badly I'm going to fix it here. Okay, just kind of needed to put my r on the other side of the dotted line. Now we understand that here's the r coordinate and theta is our angle as measured from the pole, rather the polar axis. R is the distance measured from the pole, theta the angle from the polar axis, and we consider the x-axis to be our polar axis. So now our typical increment down here runs between, has an interval delta theta. It comes out something like this and like this, as we've seen before. We have an arc here, and a delta r here, and a delta theta here. That's our delta r by r delta theta area increment. And above that we have a volume increment. And the volume increment is characterized also by a delta z. Not particularly well drawn, again, having a little trouble with the setup here, but we get the idea. So this is r delta theta delta z volume increment with sample point Ri star, theta j star, and zk star. Now, y is just r times the sine of theta, so that our delta function becomes delta of r theta z equals 1 plus r sine theta. I'm sure that's all on the screen. Let's make sure. Okay, so the delta function transforms into polar coordinates just by allowing y to equal r sine theta. And our coordinate system will now consist of r theta in the horizontal plane we regard as the horizontal plane, and z coming up perpendicular to that plane. That's called a cylindrical coordinate system. Now, as before, we can multiply our density, and I suppose that I should have, no, what I've got there is fine. Our density, which is our delta of r theta z function of 1 plus r sine theta evaluated at ri star, theta j star, zk star. Of course, that's going to be 1 plus r sub I sine theta sub j. We're going to multiply that by the volume of our increment, and we're going to get the mass. If we want to calculate the moment of inertia, we just need the distance from the z-axis to this point, but from the z-axis to our sample point, we have a distance that's simply congruent to this segment here, which has a length r, so that once more we have, and we'll call that ri star, from the z-axis. Putting all that together, we find that the the contribution to the moment of inertia is delta mijk times ri star squared, and that's going to be our delta I, our contribution to the moment of inertia for the ijkth increment of the partition. So that delta I sub ijk equals our density function evaluated at our sample point. That's going to be 1 plus Ri star sine theta j star multiplied by, ultimately by our area, or our volume increment, and that would give us our mass, and then we're multiplying that by our distance squared, which is just Ri star squared, and then that's times our volume increment, which is r delta theta delta z. If I'm referring to this specific volume increment at this sample point, then I need to call that r sub I star delta r delta theta delta z, so that I have volume increment Ri star squared delta r delta theta delta z.